This information is brought to you by Charles Sturt University.
Hi, this is a little example on how to do some line integrals when you've got 3 dimensions. So here we've got a situation where we're in 3D and our curve is a circle with radius 2 at a height of 2, so it's sort of circle sitting in place. We've got some 3-dimensional vector field, so xz, xz, yz are the different components. We want to find the integral by integrating this curve, should we do orientation, so anti-clockwise from above. So what I mean by that is, you're looking from above, so higher up, higher z values, well, it looks like anti-clockwise. So how to work this out? Well, the strategy is similar to when you've got line integrals just 2 dimensions, and that is the first thing you do is check if it's closed, a curve. In this case, it is a closed curve, so that's great. If it wasn't closed, then you check if it's conservative. If it's conservative, then you can do the fundamental theorem of line integrals. If it was neither closed nor conservative, then you have to parameterize the curve and work it out directly. So in this case, it is closed. So what do we do? Well, we like to do something like Green's theorem. But Green's theorem is only suited directly for 2 dimensions, but you can choose the generalization of Green's theorem, and that is to use Stokes. So we're going to use Stokes' theorem. So Stokes' theorem is really just the Green's theorem for 3 dimensions, is the basic idea. So Green's theorem states is that so long as the orientations, you have to get the orientations all lined up, but the line integral around this closed curve is equal to the double integral over the enclosed region. So let's give it a name. So the enclosed region is, say, the disk. So it would be the disk. Oops, the highlighter not working. So it would be the disk D, which would be, say, x squared plus y squared, all shaded in, so less than or equal to 4, z is equal to 2. That's my closed-in region. So the line integral around a closed curve is equal to the double integral over that whole region of the curl of f dot times by dA. Or let's say more general terms, ds is the more general thing. So capital S indicates surface area, a little squiggle underneath it to indicate that it's, get the sense that I'm looking at the component of this perpendicular to the surface. That's what I mean by dot ds. Now, that's just shorthand notation for a flux integral. A flux integral, as always, is shorthand notation for the curl. So the first bit's the same. The dot ds bit is really just shorthand notation for dot the unit normal times by a bit of surface area. So you can see one here. If I wrote it out tight, this first would over here be bold. This one's a normal type, and it's just shorthand notation for it. So the reason why we use this first notation, why do we always write it out that, is because sometimes the unit normal is straightforward to work out, and you'll just expand it just like I've done here. At other points in time, the unit normal is not straightforward to work out, and therefore you have to parameterize the surface in terms of 2 parameters. And the way you do it is you get slightly different formulas cropping up. So whatever you end up, capital N is how I've described it elsewhere. So dot capital N with squiggle underneath it, and D, the 2 parameters, so D, du, or D and D what, du, dv. For example, if there was parameters u and v in general, commonly you make them into x and y in this case. Now in this situation, it's a nice circle sitting in the plane. So the unit normal is going to be pretty easy to work out, so I can write it up. So it's going to be, the normal is just going to be pointing the positive y direction, which is just k. Now, why do I know it's going up? Why is it not going down? Well, because it's anti-clockwise. So if you get your fingers and curl them round, this is on your right hand, so it's right hand rule. So curl your right hand fingers around, then your thumb point in the direction of the normal. So it's my right hand. Now let's just draw the rest of the hand. So it's just my fist essentially. They're my fingers curling around. That's my thumb pointing up. So I can tell the unit the normal's going upwards. So in this case, this formula is going to work out quite nicely. So it's putting a step back, because it's closed curve, we know to use Stokes' theorem. So I just write down that result essentially. And when I see that, you go, well, let's just take on its own merit. So I work out what the curl is, look at the surface, you go, well, the surface is nice flat, I can work out n, so I'll work out the flux integral, that particular method. If when you draw the surface, you go, well, that's pretty complicated looking, I think I better got to parameterize the curve, then you do n ds. Now, in order to do this, because we can choose whatever surface we wanted to colour in, we might as well make it as simple as possible. And so when we use Stokes' theorem in this direction, you're choosing the surface so that the unit normal is straightforward. And therefore, that is a nice way of doing it. By the way, you can use Stokes in the other direction, so you can work out a double integral of curl dot ds to go into a certain line integral. That's something doable in certain situations. That's something interesting. And again, just take the line integral that you produce on its own merits. And indeed, the way to do this line integral you might use Stokes' theorems again, but using a different surface, one where n is easier to work out. But anyway, this particular case, to proceed, we need n done. So n's k. Next thing we need to work out is the curl. So let's try to work this one out here. So the curl of f. Now let's remember the way to remember how to do curl is take the cross product of nabla, which is basically a bunch of differential operators del x, del y, del z. Take the cross product of that and the vector k, the vector field capital F. So what I take cross products again, just another memory device is write down the components of partial derivatives, then the components of f, which is in this case xz, xy I should say, xz, and xy, and yz, right up the top. Yep, that's what I mean. So just copy those down, and then just use the normal rules for taking cross product. So takes a determinant now. So the component of I would be take this one. So del y of yz times del z of xz. So it's del y of yz minus del z of xz. And what I mean by del y is just shorthand for saying partial derivative of respect to y. That's the I component. Let's work it out. I mean, there's a few more terms here. So del y del yz is going to be equal to just z. Del z of xz is going to be x. We've got all right. So it's going to be y minus x I. Next one. Try to draw some nice marks. So you wipe out the y. You do the cross terms. It's a minus sign, and so I'll do minus of del x yz minus del z xz. That's the j component. You alternate signs when you're going across the determinant. So del x of yz is going to be nothing. Del z of xz is going to be minus x. And minus minus gives you positive x. J I should say. And the last term is the k. So we just cover up the row and column containing k. And so we've got plus del x xz minus del y xz, and that's the k component all up. So del x del xz is going to be just z, and del y xz is going to be nothing. So the curl in this case is these three components. And again, you can easily write down that in sort of bracket format, same sort of idea. So they mean the same thing. So now we've got the curl, now we've got the unit normal. As you can see, before we do the integral, we might as well just do the dot product. So we want to take the dot product of the curl, which we've just worked out, and the unit normal, and let's remind ourselves the unit normal was equal to the pointing up in the positive z direction, so just k, and which you can write down as 0, 0, 1, if that's helpful to remind yourself. So the dot product of that vector and that vector is just going to be, well, 0 times this one, nothing, 0 times the second term, nothing, and 1 times by z. So just going to equal z in this case. And so our line integral, which we're going to work out, by Stokes is equal to the double integral over our disk sitting up in there in space of this particular cross product, that's the component, that's z, dA. Well, however, exactly as it says, ds, the S stands for surface area. Now, in this particular case, let's think what d is. So d, as you can see, this light shaded is the green shaded disk. Basically, is a disk sitting where z is equal to 2. So in this case, the z is actually equal to 2, and I can factorise the 2 right out even. So it's the double integral of d capital S. Now, capital S being the surface area. Now, often when we have surface area of a flat plane, that's just a bit of area, just a simple area, no curvature at all, I would sometimes write capital A, indicate the same thing. But nevertheless, when we're doing a double integral where there's no integrand whatsoever, just a 1 really, then that's just going to simplify down to just the surface area, or the area of our surface. So the double integral of 1 dA or ds is just going to be the area of that particular region. And because it's just a nice little circle, it's very straightforward, so it's going to be pi r squared. And so we're getting 2 times 2 squared, it gives you 8 pi. So that gives you an idea of how to do Stokes theorem, or one way of using Stokes theorem, going from a line integral into a double integral. But you can do it backwards as well in other implications, but shows you how you do Stokes theorem. And I hope that helps.